Standing waves in an open-ended tube. This is both ends open. Alright, so in our lab, we found that the first harmonic looked like this. Now, it was hard to see, right? We really found it through comparing the wavelength to the length, and we found that the physical length of the tube was half of the actual wavelength. So, here's that in words, alright? And the key thing here is in order to draw 1/2 of a wavelength, alright, the end of the tube must be an antinode. So in this case, both ends are an antinode, in which case there's only one node in between, so you have half a wavelength. Now, the second and third harmonics, right, the second harmonic, I'm going to have 2 nodes, but the ends still must be antinodes, so it looks like this. And then the third harmonic. So comparing this to waves on a string, you can still see that the second harmonic has 2 loops, except the second loop is split between the ends. Same thing with the third harmonic. 2 full loops and then 2 half loops makes a total of 3 loops. So that leads us to the equation that we're going to use to find the wavelengths of the harmonics. Alright, so it's actually the same as for a string fixed at both ends, which we've done before. Alright, so lambda, or the wavelength, is going to be equal to twice the length divided by the harmonic number. Remember that the wavelength can be any positive number, the length is a positive number, and n is the harmonic number, which just has to be a positive integer.